Hi everybody, I hope everybody is doing well. So the goal of this lecture will be to discuss some examples about inner products. Again, for best understanding of this lecture, please read lecture notes of March 26th and March 31st. So the examples will make most sense after reading these notes. Okay, so let me recall the definition of an inner product. So throughout is going to be a real vector space finite or infinite dimensional, we don't know that. So an inner product is a map from V cross V to R satisfying certain properties. So the first of these is about linearity in one of the entries. So C1 V1 plus C2 V2 inner product with W, let's say, is equal to C1 V1W plus C2 V2W. This holds for all C1, C2 in R and V1, V2, and W in V. So this is saying the inner product is linear in the first entry. That's the first condition. Now the second one is symmetry. VW is equal to WV for all VW in V. Now if you think about 1 and 2 together, so this implies that you have linearity in the second entry as well. So let me write that here. This is not a rule, but this is a consequence. So and 1 and 2 imply, if you do this, then you can separate again linearly. So C1 VW1 plus C2 VW2, again for all C1, C2 in real numbers, and the others are vectors. Let me not write that. Okay, now there is one more important condition, condition 3. So a vector inner product with itself is always greater than or equal to 0. Well, since the field is real numbers, this is meaningful. Furthermore, equality happens if and only if the vector is 0. Well, I should stick in a for all V in V here. And furthermore, equals 0 if and only if V is the 0 vector. Well, okay, if V is the 0 vector, it's not hard to check by the linearity rules that you should get 0. But the other one is not automatic. I mean, this could be equal to 0 with the vector not being 0. Actually, I'll show you a concrete example soon. So any product like this, which satisfies these rules, is called an inner product on V. the same vector space could carry multiple inner products, and essentially how you should think about it is if you change your inner product, you are changing your notions of length, angle, and similar things. Okay. Now, the standard example, well, it's called the standard inner product. On V equals Rn, okay, is the direct extension of the dot product in 3 dimensions. So it's, so you have a vector with components a1 up to an and b1 up to bn here. You just multiply the corresponding components and add these up. Okay, this gives you an inner product. Let me leave to you to check. It's very straightforward. In the last part, you'll use that the sum of squares is always non-negative, etc. Okay. Now let's do a more interesting example. Just to keep things simple, let's VB are two dimensions, and let's select and fix a certain real number k. So, okay, the formula I'll write will involve k. Okay, so here's the question. Let a1, a2, product b1, b2 equals, okay, a1 times b1 plus k times a1 b2 plus a2 b1 plus 3 times a2 b2. Okay? The question is, for which values of k is this really an inner product? Okay. So what's happening here? Now, let me not spend too much time, but if you think about it for a few minutes or write it down, you'll see that the rules 1 and 2 are clearly satisfied independent of what k is. So it's easy to see. That conditions 1 and 2 for being an inner product are satisfied for any k. We just write it down, write linearity down, it works out. Let me not spend time with that. Now, the more interesting part is number 3. This non-negativity business. So that's not automatic at all and not true for certain values, so let's check that. So say, let's select an arbitrary vector, say a1, a2 in R2, right? We should look at V inner product V, right? Okay. V inner product V, well, you have to do that. Then apply the formula. I'll write the result for you. You'll get a1 squared plus 2k times a1, a2 plus 3a2 squared. Okay, and we want this quantity to be non-negative, greater than or equal to 0 for all a1, a2. Oh, that's a strong condition. You have some quadratic equation and you want that to always give you non-negative results. So if you remember a little bit about quadratics, well, your experience with parabolas and stuff, well, this happens if and only if the discriminant is negative. Well, I have to add something to this, but let's write the discriminant first. It's the middle coefficient square for k squared minus 4 times the first coefficient and the last coefficient, which is 12. This should be negative. Now, I'm sorry, so I wrote greater than or equal to 0, then I have to write here less than or equal, but I have to make some correction about equal a little bit later. Okay. Now, why is this true? Let me repeat. So, the coefficients of a1 squared and a2 squared are positive. So, I mean, this is like a parabola with arms going up, and it's not going to cross the axis precisely if the discriminant is negative. Well, if the discriminant is equal to 0, it could touch the axis and go back. We'll think about that. But first of all, this condition says k squared is less than 3, so absolute value of k is less than or equal to square root 3. Okay. Now, what about delta equals 0? I mean, there's a problem here which I want to explicitly show you. In that case, a1 squared, well, if delta is equal to 0, by the way, k, absolute k is equal to square root 3. So you have a1 squared plus or minus 2 times root 3 a1 a2 plus, let me write the last one as square root 3 a2 parenthesis square. And you would immediately realize that this is a complete square, a1 plus or minus root 3 a2 square, right? It is true that this is greater than or equal to 0. No problem about that. But if you remember back this last piece of the definition, let me go back here to the definition of inner product, this furthermore part. You want equality to 0 if and only if the vector is 0. But this is not what's going to happen here. Now, in our example, if delta is equal to 0, then this is greater than or equal to 0, but it can still be 0 even though a1, a2 is not 0, 0. For instance, I mean, just to give a concrete example, a2 is equal to 1, a1 is equal to minus or plus root 3, depending on this is plus or minus. So, the conclusion is delta shouldn't be 0. This is not allowed. It's only delta less than 0 which is allowed. So the conclusion is, okay, this absolute value of k should be strictly less than square root 3. That's the answer to the question. I mean, these are precisely the values of the parameter k, which give you an inner product in this example. Okay? I mean, when you change k, your inner product would change. You would have different lengths, different angles, whatever. But there's a limitation to where you can choose k. I mean, you cannot choose k to be too large or too small. Okay? Its absolute value should be less than square root 3. Okay, so let's do something a little bit different now. Let's think about orthogonal projections. Let's say revisit it. We discussed this in the lecture notes, but it's very geometric, and I think I should sort of draw some pictures. Okay, so say you have V together with an inner product. This is an inner product space. And say you have two vectors in here, V and W. Okay, now let me make some pictures as if this is three-dimensional space. Although this is completely abstract, as you know, V could be some space of functions or something completely esoteric, but still, this is just some sort of way of thinking about it only. Okay, now what I mean by the projection, orthogonal projection, is something like that. So I want this angle to be 90 degrees, and I want some projection of V along W. I'll call this proj WV. This is the orthogonal projection of V along W. This is what we want to think about it. And this vector, let's not overlook this. Well, it is some orthogonal vector to W, as you see from the figure. But just by addition rule of vectors, this is supposed to be V minus proj WV, just by tail to end addition, just we do often. Okay, now this is the picture of how to think about this orthogonal projection, but what's the algebra? So how do we think about it and how do we compute? Now, this proj WV is determined by the following two conditions. If you want, you could take this as the algebraic definition of this orthogonal projection. Okay, first of all, it should be along W, which means it should be a scalar multiple of W. So proj WV is equal to lambda times W for some real number lambda. And the second is this difference vector, whatever it is, it should be orthogonal to W. So V minus proj WV is orthogonal to W. This symbol is orthogonal to. Okay, these two conditions will determine this vector in a unique way, as we'll see in a moment. Well, first of all, what is orthogonal to? Well, 90 degrees angle, but in terms of abstractly, in terms of the inner product, it just means that the inner product of these two vectors is equal to 0. That's it. Okay, so let's forget the picture for now. Let's turn back to these conditions. These conditions determine this proj WV uniquely. Let's do that. Well, all you have to do is to write the condition v minus lambda w equals 0. Now we have linearity in the second slot, therefore I can rewrite this as vw minus lambda times ww equals 0. So there's a unique solution to this. Lambda must be vw over ww. Well, I forgot to say, but I have to say w should not be the 0 vector. Assume this in the beginning. Projection along the 0 vector. Well, okay, that doesn't make too much sense. At least it's not interesting. Let's select it to be non-zero. And once you assume that by one of the rules, this quantity is not 0. It is strictly greater than 0. So you can always divide by that number. Okay. So, by the way, this gave us the formula in a unique way. So this must be the formula for the projection. Okay, this is very nice because it's computed purely in terms of the inner product, and all you have to do is this inner product operation and division. It's quite easy to compute. Okay, now let's do one example with that. Let's do something geometric in some dimension, let's say 5 dimensions maybe. Let me try to keep this formula on the screen for a while. Okay, here is the example. Now let's VBR5, let's say, equipped with the standard inner product. Okay. Now let's L, let me say, be the span of the vector 1, 2, 3, 4, 5. So it's a subspace of R5, and actually it's a line through the origin. Whatever that means in 5 dimensions. And let's V be the vector 1, minus 1, 1, minus 1, 1, which is also in R5, of course. Now, question A. Find the shortest distance from this vector to the line. Okay, I didn't define this technically, but this is just means this is infimum of, if you like, the distance or the length of V minus W, where W is in L. Okay, actually by a small compactness argument, this is actually the minimum, but anyway. So that's the first question. And the second question is find the angle between these two vectors, 1 minus 1, 1 minus 1, 1, and 1, 2, 3, 4, 5, which generates the subspace L. Okay, for part A, how do we do that? I claim that the shortest distance is the following. So let's make a figure. This is L, let's say. Well, it is spanned by 1, 2, 3, 4, 5 somehow. You have your other vector V here. Now its projection along L will be somewhere here. Then here you'll have a right angle, and here you have V minus proj WV. I forgot to write what W was. W is this vector in my notation. So I claim that this minimal distance is the length of this orthogonal component. So V minus proj WV. So how do you prove that? It's not too hard. Well, let me say it in words and try to write it down. Select another vector along L, let's say some U. Look at the difference between V and U. You'll get some kind of right triangle here. Then you have to use Pythagoras rule. Okay, that's kind of the proof. Try to make it explicit. Now, so it all boils down to computing a projection then. So projection of V along W is by our formula VW over WW times W. Okay, now this is the standard inner product, so you just have to do the inner product of 1 minus 1, 1 minus 1, 1, and 1, 2, 3, 4, 5. Then you multiply the corresponding entries, add them up. You get something like this. Now you divide by WW, then it's going to be 1 squared plus 2 squared, 3 squared, 4 squared, 5 squared. And then you write the vector W itself. So the result is going to be a vector, right? Okay. So this is some funny rational number like 3 over 55. If I didn't make a mistake here, times 1, 2, 3, 4, 5. Okay, this is the projection. So this is the vector along L, red vector along L. This is not exactly what you want. You want V minus proj WV and its length. So you have to continue your computation. So, but these are quite routine. V minus proj WV. You just subtract. So it's 1 minus 1, 1 minus 1, 1 minus this vector here. Which you can explicitly compute. You begin to get some crazy numbers. Yeah, please double check my computations. It's just straightforward computation. Then the next thing is you want to look at the length of this vector. Again, our inner product is standard, so this 1 over 55 will come out as a common factor, and the others you have to use kind of the Pythagoras rule. I mean, just square them up, add them up, and then take square root. Okay, this is exactly a good point to use a calculator. This, if I'm not wrong, gives you something like 120.95 over 55, something like that. This is approximate, of course. So this is something like 2.20 units. Okay, this is the distance between this vector and the line. Now, compared to, let's try to see if this makes sense. Here is L. This distance is something like 220. This length of V was 1 minus 1, 1 minus 1, 1. So the length of V itself is square root 5, which is around 224. So at least it doesn't violate our senses. I mean, this length should be shorter than that one, but it's very close. So this means the angle should be kind of large. I mean, it should be close to a right angle. Let's see the angle. Okay, so how do you compute the angle? Well, we had a formula. Cosine of the angle is equal to the inner product of the vectors divided by the product of the lengths. And in this example, everything is quite straightforward to compute. Again, you have 3 here, and the lengths are root 5 and root 55. So you want to find the angle whose cosine is 3 over 5 square root 11. Of course, I cannot do this without any calculator, but with a calculator you can easily take cosine inverse, and it turns out, if I'm not wrong, something around 79.6 degrees. Okay, so it's not really a right angle, but sort of kind of close there. Okay, so this was some examples about inner products. Hope you enjoyed it. So see you soon.